Okay, 1 o'clock on US Eastern Time, and I will get us started on our next installment of the Grease Thief Thursdays. Uh, Trig Minnick is with us here. Trig, how is my sound quality for us to get started?
Sound is right on. Sounds good. Appreciate it.
Okay, great. So I'm going to start us off here today, kind of going through some of the background and uh, some information about ferrous debris measurement. And I'm going to lead us through a bit of a couple slides here to give us some information to start. And I'm going to start today by talking about asking this question: why grease analysis? Why would we do grease analysis? And it comes down to the criticality of the equipment that's being greased, and knowing that it can fail. But prior to that failure, there's going to be some information present that we can harvest, that we can look at, that we can trend, that we can put up against some criteria. And today, out of all the tests that we can do, we're going to be focusing in on the ferrous content of the grease. The one thing to consider in this process is that grease is different. And too often in doing grease analysis, it just gets treated as another version of oil, kind of a thicker oil, if you will. Uh, in grease, we've got viscosity. It's the property of the oil that sets that lubricating film. Grease is an oil, but it also has a thickener. And that behavior that we see in grease, that tendency to stay put in the machine, can be described as non-Newtonian. So grease behaves differently than oil, not only in the machine, but in how it is and can be handled for the purposes of analysis. So we can't just treat grease as if it were some other oil. For instance, we can't even shake it up to distribute the particulate that's present. And a lot of the measurements we make with oil are really dependent on the homogeneity of what we're trying to measure. And that's why we take an oil sample and we vigorously agitate that sample to evenly distribute the particulate. And in the case of grease, you can't do that. You don't accomplish much by shaking a grease sample. And so we're going to talk about some of the differences there and some of the differences in the approach and technique of measuring grease ferrous content and how that comes into play. We start with the Grease Thief sampler. We talked about this a couple weeks ago. We gave you some examples and how they can be used and demonstrated, and we'll continue to do that throughout this series. We'll bring new examples in test stands, and we'll continue to educate on the process of grease sampling. But we introduced the Grease Thief sampler here, a couple of two different versions. One on the right here that has a stinger probe, and the one on the left, which is what we might consider our standard Grease Thief. But together here, they give us this clear plastic body, a cap that keeps the grease in place after the sample's been taken, a fitted piston, and the handle. And so it's this format that we've optimized for taking the sample, that's what has become now the standard for taking grease samples, ASTM D7718. And it is also a standard unit at which we can introduce to the analysis process. And so we're going to show how we can use this sampling tool in the measurement of ferrous content. So grease analysis that you can do with this includes kind of four focus areas: the wear, the consistency changes of the grease, the measurement of contamination that has gotten into the grease, and also the oxidation or the aging of the grease itself. Now, out of these four areas, today we're keying in on the top one there, wear, and we're keying specifically on ferrous wear. So we may have some grease lubricated components that are perhaps majority or primarily non-ferrous component, brasses and bronzes and other things. But the majority of the assets that we're going to monitor for grease analysis do have a significant contribution of ferrous wear as its parts wear. So we're going to look at that as a method, a real nice screening test, a measurement test, something that we can look at over time and assess the changing wear conditions of the component. It's one of the many tests that we can do with grease analysis under the ASTM standard D7918. It was originally approved and published back in 2015. We can get 10 different tests with that 1 gram of grease. And the first one that you see here in this display is the ferrous debris. We kind of have a generic little container here or instrument, if you will, but we're going to show you a number of working units that can accomplish this ferrous debris measurement, kind of contrast and compare them a little bit, and show you the one that we're really using now going forward as a reliable method, reliable instrument for measuring ferrous debris. Uh, we share the data in a process that we call Navigator, or a system we call Navigator, and we can capture the results as well as the identifying information of the equipment and use that to trend, to create criteria, to designate samples for further follow-up, for further analysis, maybe additional sampling or more detailed testing. What can we do with this simple test of ferrous debris? Well, we get a measurement that gives us the ferrous content in parts per million as a function of the volume of grease that's being tested. And with that concentration, if you will, we can take this illustration here on the right, which is a logarithmic graph. And you can see that we've created some criteria through the use of color in this graph. We've taken different samples from different locations of the same type of asset, and you can see the groupings that we see here. Some of these sample sets, like maybe these samples over on the right, are all kind of landing in our green range here, parts per million of around 100 or less for most of them. Then you've got some that are creeping up. You've got one whole set of data here that is significantly and consistently above our green and yellow rating. So just by taking the data, putting it together as a set, and looking for these patterns, we can kind of pick out and choose those areas that may be indicative of some kind of operating condition, a maintenance process, maybe a grease that's not getting the job done, maybe the greasing process itself, maybe there's contamination issues. Whatever it is, we can use the data, kind of arrayed like this, just a single data point, and learn quite a bit about changing conditions with respect to equipment wear. In more detailed analysis, we get into presenting reports on the grease analysis, looking at all the four areas that we talked about: wear, consistency, contamination, and oxidation, and looking at all that. But today we're just going to look at ferrous debris in parts per million. So a couple of quick case studies, one from Robotics, where a number of samples are being taken from these large 6-axis robots. And I can just share some data here with you that kind of tells a story that even in an application where wear levels are consistently pretty low, you can see that in this grouping or gathering together of the data points, there's 3 locations, 3 robot joints that clearly rise up above the normal and average value of ferrous debris being generated over the operating cycle. In other words, the time between grease replenishment. This is another aspect of grease that's got to be taken into consideration, is that unlike oil, where we can create over time a certain kind of equilibrium particle concentration, where you're balancing the rate of creation of wear particles with the rate of removal, which could be settling, it could be filtering out, it could be ground up into smaller pieces. Whatever that is, it kind of strikes this balance, maybe this slightly increasing over time concentration of wear. In grease, it's quite different. It is cumulative. So from the time that we have a new grease, since we have a new piece of equipment or we've done a grease replenishment, we flushed the old grease out, took the old wear particles away, we put new grease in, we start at or near zero in terms of the concentration of wear. And after some period of operating time, operating cycles, you're going to accumulate this particulate up to the volume or the amount that you would measure. And here, with these robots all kind of operating in a similar cycle, like loading, similar environmental conditions, and so on, that there are some clear outliers. So you can almost self-check or create criteria from the data set itself, provided that you do groupings of similar applications, age of the grease, and so on. Another example here from a wind turbine blade bearing, and blade bearings are tricky, right? We've got, in a wind turbine application, you got a number of components. Of course, you got the oil lubricated gearbox, but everything else pretty much is going to be grease lubricated in the drivetrain. And the blade bearings are really tough because they hardly ever move or rotate. Yes, they kind of index back and forth as needed to reposition themselves, but you don't have this kind of continuous moving and so on. So it's hard to measure their condition otherwise with vibration analysis or any of the other tools that we might think of. So grease analysis becomes very important. And just like in general examples, the particulate accumulates over time. So when we get access to the blades, we get the sample, we get a picture of what's happened over that cycle of since the last time we sampled it, since grease has been replenished, and so on. And here you can see some examples from wind turbines in a particular wind farm with about 30 different towers there. And there are three that are clear outliers of the group. And so, you know, in this case, this tower 56, for example, that's rising up above the others, it may start to have other obvious problems. It may be noisy. There may be some kind of discharge. There might be other indications that that the operator has about that, and so they would schedule a repair there and maybe order a crane to come in to remove that particular bearing on that tower. The problem is that there are two others right in that same location that are also experiencing problems that just aren't as obvious. And so if we could get this data all together through grease analysis, it may create a more efficient maintenance activity where we can check all three of these while we're out there, even the ones that aren't as obvious. And that's what the dimension of grease analysis brings that we could add and really help with our asset management approach. So I'm going to circle out of this and take my demonstration to some of the Ferrous measurement tools that we have here. So I'm going to start here down at the end, and I think that I know on my screen I've got two videos for you to be able to see, and you may have to kind of click on one here. Let's see. Well, that's an issue I didn't think about. Someone calls me in the middle of the presentation, and I can't have to answer the phone or not answer the phone to get my video back. So let's see here. Try to restore my feed, and we'll get a nice close up here. All right. So the first device we have here is the FurroCheck, I should say, FurroCheck from Spectro. This is an instrument that's been out there for a few years. It's being used for oils, but it also has grease capabilities as well. You can use this by choosing the type of application you have, whether it's oil or grease, whether it's a high concentration, low concentration, or what you expect it to be. And it's got some different ranges for that. And so we can kind of start here with the grease low setting and select that. And then we can make a measurement. So there is a standard here that I can use, and it already has the concentration printed on there. I would hit the run button. It does kind of a background timing circuit, and then I have to be ready to insert that fairly quickly after it gives me that warning. It goes through a measurement protocol here, gives me another warning to remove it, and then it goes on with its measurement. And this particular sample that I put in here is a little over 1,000 ppm, and that's the measurement that we're going to look or expect out of this device. So good confirmation to what I knew was being put in there. Now let's see if I've got a higher concentration. I could switch that out, grease high, and start my process again, get my sample ready to go. Hit run, drop that in. And if your timing is off, it might stop and tell you to do it over again. So the timing is pretty important. You got to be pretty attentive to get that right. Remove it at the right time, and then it'll give us a reading. Now, the process for this involves this material. And you can see there that time it went up the upper scale, and this went up to 7%. or something. Yeah, it says 6.9, so it's up in that range. So those are standards. Now actually do the analysis, what we have is these devices here, this plastic device, and it has a little cutout like a canoe there. And the idea is that you're going to put the grease in there, fill that up, drop that into this piece, and then that gets dropped into the sample. In a minute, I'll come back and I'll demonstrate that process for us. But I'm going to move on now to another device. And this device is the FDM. If I can get the screen there. And this device has been around for a number of years, originally made by Enelex. And the product was discontinued a few years ago and replaced by a product with quite a different measuring process. So this one has, like the first one, the FurQ has a coil inside and then a cavity that can take the sample. Now notice I used a special adapter for the FurQ because the grease thief that we've talked about does not fit into that. But the FDM that you see here can take the grease thief. It just says simply dropping that in, letting that take the measurement, and then that returns a value, in this case, out of range. So I kind of put it through a challenge. There is a limit somewhere around 30,000 for this device. So the higher concentration greases are going to be a little more challenging. I'll get an easier one for this device to be able to handle here. And this should be around 1,000 ppm or so. So we'll give it another shot. And it gives us a value of 1304. Now, when you look at the ASTM standard, it does reference this device. And for a number of years, we did a lot of research with this, some international research, especially in the wind area. And we were able to get this instrument working fairly well as a tool for this. But the problem is it's been discontinued and there isn't really a functional replacement for it that works on this principle of having the coil and then having the sample going into that entire coil. Because as I said at the beginning, you can't shake up the grease sample and you can't evenly distribute the particulate. So it creates the same problem, say, if you wanted to use a PQ analyzer. And a PQ analyzer is designed to take an oil liquid sample, you flip the bottle upside down, you put the cap on it, and then based off of the particulate that's in the field zone near that end of the cap, and because it's evenly distributed, you can measure a value, an index that will change with the concentration of particulate in the liquid. But when you put grease on there, you don't get that same opportunity to distribute the particulate by shaking with grease. So there's some question about how repeatable, how accurate is it, how representative is that, and so on. So this device, while it did well for a while, no longer being available, we need something reliable that's going to measure on the same principle, but also now be able to work with the grease thief and have that kind of repeatability and range and so forth. So takes us on to the newest version available for this process, and that's the FurQ. So I'm going to wake this FurQ up with a sample here that is 0 ppm, and it's going to take a measurement there. I can read that screen pretty well. And notice it fits in with the size of the grease thief, which is nice, and very quick kind of response. Now here's a high concentration sample. I'll drop that in, and we know that this one's a little up in the neighborhood of 60,000. So we get the value that we expect here, and we can move on. Now remember, this is the same grease thief that we tried in the FDM, and it said out of scale because its high end is about 30,000. And we can't even get to the point of measuring this initially with the spectro unit because it simply doesn't fit. The hole is too small for the grease thief, so we can't get a measurement. So what we have to do now is this process of transfer. And let's see, I got a spatula. Now I'll cheat a little bit and I'll use a second one of these units. But I would have to, this is the process that to go ahead and take a measurement. I have to take the cap off. This is probably the best way to show it up here. Take the cap off and squeeze some grease out. Then kind of smooth this out. And you could do this, they typically give you a tongue depressor to go ahead and get this smoothed out just right. So you're going to take your time and get this kind of worked out, get this amount properly measured, and then take it, put it into this protective cap here. And we knew this was 60,000, so it's pretty high concentration. We should be still on the grease high. We'll go ahead and take a measurement here. Okay. So we'll get a measurement there. But now my challenge is, if all I want to do is ferrous debris, I'm done and my sample is, I'm done with it and so forth. But if I want to go on and do other measurement, I'm going to have to dig this grease out of here, put it back into the grease seat perhaps, or somehow otherwise try to handle that. So there's a lot more handling involved, a lot more time involved to get, what I'm looking for from a sample as compared to the FurQ. And that's where we are with this now. So I've got a number of different samples here. We can continue on. One thing you'll notice is that the results here are going to be delivered by this unit regardless of the range. We don't have a high range and a low range. It's auto ranging. So we can have a sample that's a lot of debris. We had 60,000, roughly 60,000 there before. Now we have about 1,000 ppm, and we have that represented here. So the difference in the instruments is the time involved, the ease of preparing the sample, maybe the range, whether there's a single range or two ranges. So we had a single range with the FurQ. We had two ranges with the spectra that helped us get into the higher values. We only had one range with the FDM, so we kind of cut off there. From a simplicity of handling standpoint, with the FurQ and the FDM, you have the ability to drop the grease thief right in there, remove it, and go on and do your additional tests. And like we said at the beginning, you can do up to 10 different tests with the grease thief with that 1 gram of grease, so you're not consuming it. You don't have these extra handling steps. If we're back with the furrow check, you do have the process of where we've got to transfer the sample over into the specially designed sample cups and then maybe try to fit that all back inside again, which could be a bit of a challenge. So this is the process that I wanted to share with you today, which is a fairly simple process, which is just that ferrous measurement, giving us a single number, parts per million, perhaps with this device a percent above a certain value. So we'll handle those values. But being able to screen samples fairly quickly if we use a device that's giving us that quick turnaround, and also something that takes that 1 gram sample and allows us to do a bunch of different tests, do a quick check on the ferrous content, switch right back, and move on and do other tests as well. So I want to kind of open this up, see if we have any questions or anything else I can demonstrate from the samples that I've brought here today. So the question here about ferrous content that I saw was explain the difference between elemental iron that we might see on a report versus this ferrous content. And it's a really good question because they're really not measuring precisely the same thing. So if you're used to doing oil analysis, you'll see there, you'll have elemental analysis, typically inductively coupled plasma ICP analysis, maybe RDE, maybe even XRF analysis. And you'll have iron, lead, tin, you'll have different kinds of metals, copper, you'll have additives, you'll also have some contaminant type things. But in there, you're going to see you're going to see that iron, or it might say Fe, and that's elemental iron. And depending on the technique there, it's measuring what you have as dissolved content, so dissolved iron content, and small particles. Now, the size of the particle really depends on the technique. For ICP, it might only be up to about the 3 to 6 micron range that you're really measuring and reporting out in that value that you see as ppm. When you use RDE, that size range is a little bit larger. It might be up to 10 microns. XRF doesn't have that limitation, but that's not usually what we get in our reports. So if we are used to looking at it for oil analysis, or if we're seeing both in a grease analysis report, both elemental iron and ferrous ppm values, they're different in this way. Again, the elemental iron is going to be dissolved, perhaps oxidized, but small particles. On the other hand, we're looking at a magnetic technique here, or ferromagnetic technique. So it's going to be looking at particles independent of their size. However, when the iron gets oxidized, so rust, corrosive wear, and so on, it reduces its magnetic susceptibility, or really the influence it has on that magnetic field. So you have a depressed response from the oxidized ferrous content and the very, very small ferrous content, where the elemental iron is going to report those values quite well. So we get to use that as almost create an index with these two values. If the ferrous content, like from the FurQ, is very high and the elemental iron is relatively low, we believe that the majority of the particles are going to be large unoxidized wear, and that would have probably a more severe finding or recommendation associated with it. If the opposite is true, whereas the output of a FurQ or a device like it is real low and the elemental iron is quite high, we would expect that we either have dissolved or oxidized or very, very small ferrous particulate. And that could talk about the type of mechanisms that's there. If they're both pretty comparable, they're both high or low or what have you, you probably have a combination of wear, maybe not real large wear, but maybe small to maybe just medium-sized wear without a lot of oxidation. So you can see there's 3 different scenarios there, and depending on how these numbers relate to each other, we can gain some insight just by looking at these values. So thank you for that question. Let's see what else we have here. You have a baseline measurement, and what is considered low and high, or is it dependent on the customer to read the data and look for outliers? Good question from Jared there. So we've been doing this analysis for almost 10 years now, and we've looked in a lot of different applications, pharmaceutical facilities, mining applications, power generation, including wind turbines, robots. And so over time, we've developed some values that we see as being typical, and even create some general guidance for values for action, what's considered acceptable, what's marginal, and maybe what needs further look. So I say it's a combination of that, but remember that the quantity that you generate really is a function of the machine itself, but also how old is the grease, or how long has the grease been there. So if the grease has been there a real long time, just the straight up ferrous content could be fairly high, and it's just that it hasn't been replenished. So kind of tying that into the assessment is important as well. So I think the best situation is a combination of a lab that's, if you've got a lab doing the analysis, having experience looking at similar type of customers and similar type of assets, and bringing that to bear, but also the asset owner themselves being able to provide information about the operating cycles and so forth. I think you bring that together and you get the opportunity to make some really good judgments based off of criteria and how to act based on the values that you get. But remember too, Jared, at the beginning, I showed a graph that took a large data set of similar components, put them all together, and then use that to kind of create its own criteria to look for those outliers and say, what is normal under the operating conditions that I have? Now, If everything's bad, it's tough to self diagnose, right? Everything looks the same, but really everything's bad. So you may have to, at the beginning of a cycle, like we're just getting into grease analysis, maybe follow up some of these early tests with some more detailed analysis, like analytical ferrography, that says, you know what, we've got this level, it's 5,000 parts per million, but it's all normal rubbing wear. This is what we expect for this kind of grease replenishment frequency and the way this particular machine happens to wear. In other cases, you may look further and see that this is not good at all. This is a real problem, and then over time we can get even more refined about our criteria. So thanks for that question. You know, well, I missed that one on presentation mode. I'll tell you, it's uh, let's see. I apologize about the graphics, but what I will do is post the PowerPoint that I had today as a I think on there's a thing with LinkedIn called SlideShare, and you don't even have to be on LinkedIn to see it. So I'm going to post that this is a SlideShare, the information I shared today, and then you should be able to see those graphics, kind of blow them up and see everything you need to get there. And I think Chris asked that question. So sorry I didn't catch your question in the presentation, Chris, but hopefully we'll make sure that we get uh, a link to you specifically, so and anybody else after this that can go ahead and see that presentation. Anything else? So I just want to point out that, we've been at it for a while. We've looked at different instruments that are out there. We've been comparing them. There is some additional data that I'll put into the presentation that we post afterwards that we presented at the ASTM meeting, the last ASTM meeting, where we compared some of the older FDM data to the new data being generated by the FurQ. And what was really exciting for us about that was we really put it through its paces. We really looked at the effect of heterogeneity and distribution of the particulates. So just take the example where you go ahead, you take that grease sample, and you've got some ferrous content, but it's not evenly distributed over that sample. Well, we deliberately created this heterogeneous distribution where there was a whole lot of ferrous wear in one part or another part of the sample. And when we introduced that to the FurQ, we got consistently representative information back from that device, where we could almost kind of trick the FDM a little bit into missing some of that measurement because its measurement range through that coil is not as uniform as in the new FurQ device. So we're always looking to improve the approach and the technique, and we're really excited about the quality of data that's coming out of this coil that's designed specifically for this kind of measurement, how it works really well with the grease thief, and how that's going to give us reliable and trendable data going forward. You take that device and you match it up with the colorimeter that we introduced last week at the Grease Thief Thursdays. You put those two devices together and you have a real nice mini lab solution that you don't necessarily even have to bring a lab like ours into the picture until you need to. So you can see how small this and portable this device is, really easy to get where you need to set up and take your samples and then immediately go check it. Heck, you could carry them up a wind turbine, set it up, take your measurements there if you needed to, check the color, get the differential value of the color relative to the new grease that's being applied, be able to pick up things like oxidation, grease mixing, grease degradation, and all those things that are related to the visual kind of changes, and then add this ferrous piece, and you really see a big part of that picture. It works really well for robots as also. These very light colored greases like this Vigo grease or some similar greases used in robots. Really nice palette there to see those changes as the grease darkens over time. So nice solution, very portable, fairly low cost to get into the grease analysis game. And we can certainly help you get set up with that and kind of be your back end lab to help you learn the process and get started in grease analysis. So want to thank everybody that joined us today. Trig has put a couple of notices here in the conversations window. We'll try to follow up with everybody as we can to send you emails and notices of the upcoming events. And what do we have on the agenda for next week, Trig? Did we get to that yet? What can we leave as a teaser for next time out? Maybe we'll take some suggestions.
we do have one, but I'll tease everybody and I'll send it out in an announcement.
All right, and I'll also say it's if you've got an idea, if there's something you want to see next, I'm here in the lab, and we're going to kind of march you through the lab here in the coming weeks, show you the different instruments that are out there, show you what you can be using and how that can be the part of the beginning of a program, whether you decide to set up your own mini lab like you saw here today, or if you decide just to pull a few samples, send them to us. We'll be able to in the coming weeks talk about particle counting in greases, which is a thing. It can be done. It's actually an ASTM standard. We can look at particles greater than 50, greater than 25, and greater than 80 microns, and be able to understand what's the cleanliness and dryness of the new greases I have. Am I protecting my assets? We'll talk about dye extrusion, where you can measure the consistency of the grease. So all that's coming down the road. Look for those upcoming announcements. And again, thank you for joining us today. And we'll see you here again next week for Grease Thief Thursdays. Thanks.